So, recording started again. So, power down. So, if we compare what the different signals look like, I tried here to make an extreme display. And here we have Gaussian noise over a sine. And here you can see that the variance is about the same, even in the peaks and the valley. But if you look at the Poisson noise, the variance up in the peak is greater than down in the valley. So it could actually be that you, within the same image, have one behavior and the other behavior. And if you start seeing that very prominently, then you have to go. So that's actually also coming back to your question. Then you have to go for a more Poisson-oriented analysis. It's not very obvious actually in the difference, but you see that there is, if you look at the envelope of this noise, you can see that it narrows down a bit. Then we come to the salt and pepper. And here we have, in principle, a type of outlier noise. It could be that it really is peaking out to saturating the detector on very localized, or it can also have some amplitude. In this case, I have modeled the salt and pepper that if the outcome of a uniform distribution is below some lambda, then we have -1. If it's in an interval between two lambdas, then it's 0. And if it's greater than the second lambda, then you have a 1. So that's one way of modeling the salt and pepper. And lambda 1 plus lambda 2 is the noise fraction. And what it can look like is something like this, where I used the different lambdas. So I have lambda 1 is 1%, and lambda 2 is 99%. And then it comes out like this. And if we increase the lambdas, then it gets more and more noisy. And you can see that it's fluctuating between black and white pixels in the gray background. And how to handle these, that I will come to in a couple of slides. We always want to measure, so measuring how strong the noise is, yes?
Is it realistic to say that they're usually symmetric? So the bottom 5%?
Actually, it's more likely to be asymmetric. So this is one case that they have up and down. But often you only have one-sided. So you only have peaks, and not downs. So it depends on the measurement technique, but usually what you see as salt and pepper noise is one practical example I have from neutron imaging is that we have gamma photons hitting the detector, and these gamma photons come from the interaction with the material, and then we have a bright spot. And we never get dark spots because the photons, they punch out and give you a high intensity. So typically it's more asymmetric than symmetric, like I show here. When it can happen, actually, it depends on also when you see it. So if you start doing some processing, you have one reference image and one sample image, and you start doing some operation with them, then you can get pluses and minuses. But then usually with about the same distribution. So likely to be as many darks as you have brights. So, yes?
Is it possible that we do multiple enhancement?
Pardon? You can.
Multiple of them. Like we do one after another, so we do 2 of them.
So you get the cascade kind of.
Or is it not really common? Is it possible to have multiple types of noise?
You mean different noise types together?
Yeah,
or what?
then I have to use like maybe
Yes. You have a combination. Actually, the full imaging chain includes Poisson noise from the photons. It includes Gaussian noise from the thermal activities in the chip. Then you have sampling-related noise in the quantification from analog signal to digital signal, and then you can also have these spots.
Yeah, and if possible, I do multiple enhancement and the order of them matter, right?
Yes, so outlier noise you usually want to get rid of as soon as possible because they will be very annoying for other filtering types. But then afterwards, I usually take one do-it-all filter for the rest. Oh, sorry, I didn't complete this one. So the signal-to-noise ratio is in principle the ratio between the signal strength to the variance of or the standard deviation of the noise. And looking into that, in particular for the Poisson noise model, it's very simple actually. There is a relation, square root of number of photons gives you the signal-to-noise ratio. So here I have an example. I did an exposure at 50 milliseconds and one exposure at 10, or several measurements, but here you can see 10 seconds and 50 milliseconds. And if I do several measurements, you can see that this curve here actually follows square root of number of items. Or in this case, I actually related to exposure time, but the exposure time is proportional to number of events. So in Python, you have a bunch of functions. I'm not going to tell much about them, but you have to generate your own noise, because that's pretty good to have when you do your analysis or testing of your methods. And for the testing, it's also good to have ways to measure in the images, so you get the averages and the variances, min, max, etc. And all these are helpful for when you start analyzing the efficiency of your filtering.
I actually had a question.
Yes?
So, like, what is the intuition behind this signal-to-noise ratio increasing with exposure time? Is it because, like if you, like as the exposure time increases, so basically the sum of noises will increase?
In this case, that you get this square root of n is coming from the Poisson distribution. And the Poisson number of counts, the average is n, and the standard deviation of the Poisson distribution is square root of n. So that is why you get it. So when you increase the intensity, you of course also get different n's here, and that gives you this raise over exposure time. So that in principle says expose as long as you can, if you can. So that said, beam time or experiment time is precious, so you often have to do some balance to get the information you want and to get it as nice as you want. And then you have to do the balance between those.
But this curve suggests that like signal-to-noise ratio is increasing, right? Like with exposure time?
Yes, it does. And that's good. So
Okay, yeah, signal-to-noise ratio is increasing.
Yeah.
Yeah.
So I mean, if I expose at 50 milliseconds, you see that it's pretty noisy. I hope it's possible to see in the light here. And if I expose 10 seconds, it's pretty flat. So that is what you gain when you expose longer. So switching over to the filtering. So in principle, a filter is a little machine that enhances the wanted information and suppresses the unwanted information. And ideally, you want this to happen without altering the relevant features. In particular, beyond recognition, that is pulling it too far. But it can actually be that every time you do something with a filter, you actually modify the whole image. to some degree. And to kill the filter, to kill the noise, you may also kill relevant information in the image. So that's why you have to make a balance here. And we will look at that. And first of all, we look at two different filter characteristics, or basic characteristics. And one is low-pass filter. And in principle, what it's about, it's if you look at the frequency distribution in the image, you have slow variations at low frequencies, and you have fast variations at high frequencies. So looking at this example, you can see that I have an overlay here. One is a slow variation, and then I have some rapid fluctuations within it. And the ideal low-pass filter, this is just generated, but the ideal low-pass filter would extract only the slow variations in the image. And this makes it a useful tool when you want to remove noise, because the noise is from pixel to pixel or few pixels range. It fluctuates a lot, while normally your relevant information is more widespread, and that's why the low-pass filter is used for noise reduction. The high-pass filter is naturally the opposite. So if you may have some inhomogeneous fluctuations in your image, a high-pass filter could extract the rapid changes, and then you get something like this high-frequency plot after a high-pass filter. I'm going to the details of these soon. And the basic filters that we are working with are linear filters, so it's based on the convolution. And typically you have some convolution kernel, which is the filter description, and you have your function, and then you run a convolution over that. And if you want to see more about a convolution, there is a very nice video. It actually goes towards probability computations, but anyway, the convolution is described in 1 Brown 3 Blues. Actually a very nice source if you didn't know it before. They talk about many interesting topics in a good way. And looking at some kernels, so this is the part of the filter that actually does the operation. We have two classic filters that are used a lot. One is the mean or box filter, which is in principle a neighborhood around the central pixel, which has the same weight in the filtering. The other one is the Gauss filter, which has the shape of a Gauss bell, and both are used for suppressing noise. And looking at the effect, what we can do with the Gauss filter, here I have some examples. Test image, which is originally looking like this, and then I add noise to the image to achieve signal to noise ratio 10, 5, and 2. And you can see that in the case of 2, the original image is pretty much buried in the noise. Now, if I apply different filter strength, you can see here on the original image what happens if you make a wider or stronger filter. You can start see that you get some blurring here, and if you have a very wide filter, you can see that the blurring is actually starting to remove relevant features in the image. So if you look at these, you say, why do you want to filter at all? The other one was pretty good. But if you go to decreasing signal to noise ratio, you can see that the noise in that one is pretty good removed already in this case. Here, well, you still get the blurring. But in the really bad case of low signal to noise ratio, even the small filter is not even able. You can see the contour of the object, but not very much more. It may be sufficient for you, but mostly you want at least to see the features. If you widen the kernel and make it stronger, then you can get a better contour. You can even see that there is actually an arm here. But still, if you filter too much, it's usually the effect that you lose relevant information in your image. And a little bit a toy example on how the convolution is computed. You never have to do this in real. It's already predefined functions in Python. But what you do is you have an image. So this is an example using the box filter. You extract a neighborhood around a central pixel, sum all the pixels, divide them by 9, and you get the average value. And that is what comes into the resulting image. And depending on the size of the filter kernel, you get more elements in the sum. And if you would have a Gauss filter, then you would have to put a little weight on each of these contributions, and then finally you get your result. And yeah, so that is how it works. But there are filtering functions already implemented. So implementing this on your own is more for your own testing and playing if you enjoy the challenge of implementing it. One interesting thing about the convolution is that you can separate the kernels in some cases, and that is actually promoted by that you have the commutative and associative laws applies to the convolution. So these two expressions are the same and same as these two expressions, and that is something we can use. For example, in the box filter, you can see that we have this kernel of 3 by 3. It can actually be divided into two parts, which has less weights. And also the Gauss filter can also be split in one part, which is in the direction of horizontal direction, and one part in the vertical direction. And the gain of doing that is, if you have small kernels, probably not very much. So you can see here, if we have a 3 by 3 kernel, you should have 9 multiplications and 8 additions. And through the separation, you can get 6 multiplication and 4 additions. Not so much gain. If you go in 3D, yeah, then you can actually get, you should have 27 multiplications and 26 additions. And that is now reduced to 9 multiplications and 6 additions. Starts getting somewhere. If we increase the n, then you can start seeing that in the 3D case, you should have 125 multiplications, and that is reduced to 15. And then you start seeing some gain. This is, however, in theory, because the computer and the programming languages have their overhead, and calling 3 convolutions in a row has some computational overhead. And to see in which cases it actually makes sense, you have to experiment a little bit. Sometimes it's actually faster in practice to do this one than to do that one. So there you have to actually test and see if it makes sense. So for example, if you would have a Gaussian kernel, there usually, if sigma goes up, you have to make a very wide kernel. Then it can make sense. If you would have a 3 by 3, I wouldn't do the separation. So it's a trick that you can use to speed up your computation if you have very many images, and then it can actually bring something. Another filter that we are looking into is the median filter, and that is doing also scanning the image in the same way as you did with the convolution, taking pixel-wise. You also extract the neighborhood, but in this case, instead of computing the average or a weighted average, you sort the pixels in the neighborhood and take out the mid piece, so you get the median, and that is what you put in the next in the resulting image. The benefit of it is, in particular, when you have the outlier noise. So when you have spots, this is a spotty image. I don't know if I added the spots or not. No, it looks actually like a measured image. No, sorry, it is generated. So I added outlier noise, so salt and pepper noise. And then I tried running it with a Gauss filter, and I applied a median filter. And when you see, the Gauss filter is weighting all the pixels in the neighborhood, so if there is an outlier, that one will still come into the filtered image. If you do the median, the outlier in the sorting is usually out on the edge, so it will not be included, and then you see the very nice effect that you can remove this noise, the spotty noise, with the median filter. If you have Gaussian noise, which is not that extreme in terms of outliers, the Gauss filter tends to give you a better filtering effect than the median filter. That is actually blurring a little bit. Around the edges, the median filter may be better, but the noise cancellation effect from the Gauss filter, I would say, is better. And not to make the confusion, we are talking about Gaussian noise and Gauss filter. They're not related. So it's not that the Gauss filter is the solution to the Gauss noise. It's just the shape of the filter that has the Gaussian bell shape. And the distribution of the noise has the Gaussian bell shape. But they're not related in that sense that that is the cure for Gaussian noise. So a little filter example. We have in our neutron images a lot of spots. So when we look at an image, we have all these little outliers, and we want to remove them from the images. And amount and size varies a lot. And you can even see here that some are really localized spots, some are a little bit larger, and there are even cases when you have streaks like this. And those are very annoying in the next processing steps. If it is filtering or reconstruction, tomography reconstruction, they will introduce new artifacts. So our filter options we have here would be to apply a low-pass filter, as we have seen already. And the other way would be to take a median filter, which we saw is good to remove outliers. What I'm going to show here in this example is actually a little bit more advanced algorithm that first detects the spot and then replace it by some estimate. Reason to do it more complicated, I will show. But first, the algorithm. The algorithm is in a couple of steps. First, we do some median filtering. We subtract the median from the original, and with that, and we compute the absolute difference. With that, we get, in principle, an image where you only see spots, nothing from the image itself. And here, we do some thresholding. If the spot amplitude is above or below a threshold, you do either you replace them by the median, and then you get those localized pixels replaced. Or if you have below the threshold, then you just keep the original, and in the end you get the cleaned image. This shows up here where we have our original image. I try doing just a box filter for smoothing. I try a median filter, and I try the cleaning algorithm. So what you see here in the output first is when you look at the box filter, you even see the boxes in the filtering when you have these outliers. So that we can reject as a relevant method. And if you do the median, you see that there is some blurring in it. There are some features here that are a little bit blurred. So maybe that's also not a good solution. And finally, using this cleaning algorithm, we have essentially the image as it was in most pixels, but on the places where there were spots, then it's actually cleaned the spots. And looking at the difference between the original and the different filterings, you can see here the effects of the box filter. You really see the bad blobs. The median filter, you see that it actually also removes some other noise and possibly some structures, but the final algorithm here only removes. Yes?
Sorry, when you identify the pixels above the threshold, like the outliers,
Yes.
what value is that replace it with?
I'm replacing it with the local median. So I'm taking, so going back to this one, I'm actually bringing in the median here. So I do a mix. So this is a 1 and 0. And on the places where you have the spots, then you just bring in the median value. And that's a quite good result. Meanwhile, I have more advanced methods, but this is the, say, base method for this kind of replacement. And I don't know if any one of you are using the tool ImageJ, which is actually a pretty nice tool for initial analysis to do some exploring of the data. Some people actually use it even for mass production because it allows some scripting. But for the outlier removal, it has two options. One is despeckle, and the other one is remove outliers. Despeckle is in principle the median, so I recommend not to use it. Remove outliers is a variation of this algorithm that I showed here. So it's about this algorithm that it's using. And with a little bit minor changes, but the principle is the same. So that was it about the low-pass filters. So now we switch to high-pass filters, and we have different types of high-pass filters. Now we want to emphasize the rapid changes in the images. And what we have are gradients of different types. They can be defined in different ways. The very simple gradient is just the difference between the two neighbor pixels. But that one has its issues when you want to compute the local orientations. So in the book of Jane, this model here is proposed, and that is better if you want to compute the local orientations. Another one is to compute the Laplacian. So in this case, you have the whole neighborhood around, which is positive, and then you have a minus, which goes deep in the middle. And that computes the Laplacian of the image. Another one is the Sobel filter, which is the magnitude of gradient. And that one is also used as high-pass filter. So now you see a lot of gradients, but what actually it does to your images is shown here. We can actually see where you have edges in the images. So by orienting this kernel in different ways, so here you see you have vertical columns with the filter weights, and here you have the rows with the filter coefficients. And by running this, you have here an example, an original image. And if you run the DX, you see all the vertical edges in this image. Now at this light, it's maybe not so visible, so maybe you can see it better on the slides or in the notebook if you look at it later. And if you look at the Y derivative, then you can see that it's all the horizontal lines. With this gradient, you also get dark and bright stripes. So for the rising edge, you get the dark, and for the falling edge, you get the bright. And that is how this filter is defined. And the other way would be to look at other of these filters. So we have the Laplacian and the Sobel. And again, you have in the Laplacian you have dark and bright, but now you can see you get both directions in this edge filter. And with the Sobel, sorry for the darkness, but here you can see actually that there is no negative value in the Sobel filter. So it really extracts the edges as a single value. So this brings us to more advanced algorithms that identify edges. And depending on how the algorithm is defined, you may want to use the Laplacian filter or the Sobel filter, because with the Laplacian you can actually tell from which direction you approach the edge. So is it from dark to bright or from bright to dark? Yeah, and the Sobel, you just detect the edges. So the Sobel filter is pretty straightforward. You just threshold this image and then you have all your edges. Then in machine learning, the neural networks that do image processing, actually, they are often a type called convolutional networks, which means that these neural networks, they are a big collection of convolutions with different kernels, and each kernel is responsible to emphasize different features in the image, different orientations or different patterns, and depending on how deep in you go in the network, it doesn't look very much like images anymore, but for the network it makes sense, and in the end, in this case, it wants to identify speed signs. So here in the end it gets a selector, which is the most likely outcome of a sign. And as the bell rang, it's time for a break.